Hello guys, welcome back to my channel Algorithm Avenue. In this video, we'll be discussing about another important topic called optimizers. Okay, these optimizers are used to improve the performance of the model and also speed up the training process. Now, before discussing about these optimizers, first let us see where actually these optimizers are used in an artificial neural network. Okay, now let's say we have a data set which contains two features named f1 and f2, and this is my true output. Okay, now I want to train an artificial neural network on this data set. Okay, this is my artificial neural network. Okay, now I want to train this artificial neural network on this data set. Now what actually this artificial neural network does is it produces an predicted output called y hat. Okay, it produces an predicted output called y hat. Now in this entire process, the role of this neural network is to bring close this predicted output and true output. That is, predicted output must be nearly equal to true output. Now, in doing this possible, okay, in making this possible, there involves weights and bias values. Weights and bias values. Okay. Now, in this entire process, what actually happens is this weights and bias gets updated to make y hat value nearly equal to y value. That is, predicted output must be nearly equal to true output by updating the weights and bias values. Okay, now how this process happens is, first we send the first row of data. Okay, let's imagine we are sending the first row of data. Now when we send the first row of data, we'll be getting this y hat output. Okay, we'll be getting a predicted output. Okay, this is my predicted output and this is my true output. Okay, now I'll be calculating the loss between this true output and predicted output. Okay, okay, we'll be taking another assumption, that is, let's say in this entire neural network we are having only single weight. Okay, only single weight, that is w1. Okay, for simplicity purpose we are taking only single weight, that is w1. Okay, now we'll be plotting a graph between this loss and w1 value. Okay, we'll be plotting a graph between loss and weight values. Okay, now at the initial stage of training, okay, at initial stage of training, this loss would be definitely higher. Okay, loss is higher and correspondingly this is the value of the weight. So slowly what happens is this loss get reduced and this will be my curve. Okay, this is my curve between loss and this w1 value. Okay, this is loss and this is corresponding weight value. Okay, this happens for every epoch training. Okay, we are plotting this graph for every epoch training. Okay, this is my graph. Okay, this is an assumed graph. The graph may be in this way or it may be in this way. Okay, these are the general curves that we will be seeing between the loss and trainable parameters graphs. Okay, now let's say this is the graph. Now this is the global minimum point. Okay, this is the global minimum point where my loss is minimum. Okay, now I need the weight that is corresponding to this global minimum point. Okay, I need the weight that is corresponding to this global minimum point. So here comes our gradient descent algorithm. Okay, what our gradient descent algorithm does is, it may start from here or it may start from here. Okay, at the initial stages, okay, the initial stages, it takes longer steps. As it reaches this global minimum point, it starts taking smaller steps. Okay, much smaller, much smaller, and when it reaches this global minimum point, it gives out this corresponding w1 value. This is the optimum weight value. Okay, this is the optimum weight value. Okay, first it starts from here, it will take some longer steps, and after taking the longer steps, after it reaches this point, this is my optimum weight value. Okay, it returns some optimum weight value. Okay, how this process is done? By updating the weight values. Okay, w new is equal to w old minus learning rate dou l by dou w old. Okay, based on this learning rate, my weights are updated. Now when my weights are updated, my loss gradually changes. Okay, when my weights are updated, my loss also gradually changes. So in this way, gradient descent with help of this formula, it reaches this point. Okay, it reaches this global minimum point and returns optimum weight value. Okay, now in this entire process, gradient descent works as an optimizer. Okay, gradient descent works as an optimizer. Okay, why it is called optimizer? Because it is optimizing. Okay, it is optimizing the weights and bias values. Okay, it's optimizing the weights and bias values and finally returning our optimum weights and bias values. Okay, finally returning our optimum weights and bias values. So that is why this gradient descent is called an optimizer. Okay, this gradient descent is called as an optimizer. Okay, now this gradient descent has three variants in it. Okay, first we'll be having batch gradient descent. Second, we'll be having stochastic gradient descent. And third, we'll be having mini batch gradient descent. Okay, now let's take an overview of these three types of gradient descent. Okay, first let's take batch gradient descent. Okay, now what we do in batch gradient descent is we consider entire row of entire row of data. Okay, let's say we have 1,000 rows. Okay, we'll be considering all this 1,000 rows as a single batch. Okay, all these 1,000 rows are taken as a single batch and we'll be passing it through an artificial neural network. Okay, we'll be taking this 1,000 rows of data and we'll be passing this through artificial neural network. Now after passing it through the artificial neural network, for each row of data I'll be getting predicted output. Okay, for each row of data I'll be getting predicted output. Now finally I'll calculate the loss between this predicted output and true output, and at the end I'll be calculating the average loss, that is cost function. Okay, that is cost function. Okay, now for an epoch, okay, for an epoch I'll be doing this entire process. Okay, in just one epoch I'll be sending this entire data through the artificial neural network and I'll be calculating this cost function and I'll be updating the weights. Okay, now to update this weights, my neural network is taking the help of entire data. Okay, my neural network is taking the help of entire data. Okay, that means one epoch, in a single epoch I'm getting one update of trainable parameters. Okay, in single epoch, okay, in single epoch I'm updating the weights and bias parameters only single time. Okay, only single time. Okay, now let's see what happens in case of stochastic gradient descent. Now in stochastic gradient descent we'll be taking each row of data. Okay, now in an epoch, let's say first epoch I'll be I'll be taking first of data and I'll be sending it through the artificial neural network. I'll be calculating the y hat output and I'll be calculating the loss between the y and y hat. Okay, now this loss is stored. Okay, this loss is stored. Now the second row of data. Okay, second row of data goes into this artificial neural network. Again, the loss is calculated. Okay, again the loss is calculated. Now after sending the first row of data, after calculating this loss, the weights and bias parameters are updated with this formula. Okay, now after the first epoch training, my weights and bias parameters are updated. Sorry, after the first row of data is sent through the artificial neural network, my weights and bias parameters are updated. Now the second row of data, okay, so the second row of data goes into this artificial neural network. Again loss is calculated, again weights and bias parameters are updated. Now let's say we have 10 rows of data. Now the weights and bias parameters are updated 10 times because we have 10 rows of data. The weights and bias parameters are updated 10 times. Okay, that means one epoch is equal to 10 updates. Okay, one epoch is equal to 10 updates. That means multiple updates. Okay, not 10 updates but multiple updates. Okay, how many rows are there? That many times we'll be updating the weights and bias parameters in a single epoch. Okay, this is stochastic gradient descent. Now let's discuss about mini batch gradient descent. In mini batch gradient descent, now let's say we have 100 rows of data. Okay, now let's say batch size is equal to 5. Now 100 divided by 5. 100 divided by 5 is equal to 20. Means we'll be having 20 batches. Okay, we'll be having 20 batches, each batch containing 5 rows of data. Okay, each batch containing 5 rows of data. Okay, each batch containing 5 rows of data. Now we'll be taking this 5 rows of data and we'll be sending it through the artificial neural network, and we'll be calculating the loss for all the 5 rows. Okay, we'll be calculating the loss for all the 5 rows, and we'll be updating the weights and bias parameters for all the 5 rows at once. Okay, we'll be calculating the average loss for all the 5 rows, and we'll be updating the weights and bias parameters. Okay, now like that we'll be updating 20 times. Okay, as we have 20 batches, we'll be updating 20 times. Okay, as we have 20 batches, we'll be updating 20 types in a single epoch. Okay, this is mini batch gradient descent. In batch gradient descent, per epoch we'll be doing one update. In stochastic gradient descent, per epoch we'll be updating how many rows of data is there, that many times we'll be updating. And in mini batch gradient descent, we'll be updating multiple times. Okay, how many batches are there, that many times we'll be updating weights and bias parameters. Okay, these are three optimizers like gradient descent. Okay, these are three optimizers like gradient descent. Okay, even these three are optimizers. Okay, these three are optimizers. Okay, batch gradient descent, stochastic gradient descent, and mini batch gradient descent are optimizers. Okay, now you may have a doubt that I have these three optimizers functioning well. Now what is the necessity of other optimizers like adamoptimizer and Adagrad? Okay, now what is the necessity of those optimizers? Okay, now we'll be discussing that in the next section of the video. Now let us see few drawbacks of different types of gradient descent algorithms, so that the following optimizers have been introduced. Okay, now let's start with learning rate. Okay, you might have seen the learning rate while we update the weights and bias values, right? This variable is referred as learning rate. Okay, now this learning rate plays a crucial role in gradient descent algorithm. Okay, this learning rate plays a crucial role in gradient descent algorithm. Now let's say we have set learning rate to be higher. Now when the learning rate is higher, the gradient descent algorithm takes huge steps. Okay, this learning rate is higher when the gradient descent algorithm takes huge steps. Okay, it takes huge steps and will never reach this global minimum point. Okay, now to solve this, we'll be setting the learning rate as smaller. Okay, now when we set the learning rate as smaller, the gradient descent algorithm takes very smaller steps. Okay, it takes very smaller steps, and to reach this global minimum point, it takes larger time. That means the training time increases. Okay, that means the training time increases, but finally the gradient descent algorithm will reach this global minimum point after a longer time. Okay, after a longer time. That means we need to set some optimum value for this learning rate. Okay, we need to set some optimum value for this learning rate manually. Okay, we need to set some optimum value for this learning rate manually. Okay, this process must be done manually by testing out different learning rates. Okay, now the second problem is fixed learning rate. Okay, now the problem with fixed learning rate is, let's say this is the gradient descent curve. Okay, now the gradient descent algorithm must start from here and to reach this global minimum point. Okay, this is the global minimum point. To reach this global minimum point, initially it must take larger steps, and as it nears this global minimum point, it must take some smaller steps. Okay, initially it must take large steps, and as it reaches this global minimum point, it must take smaller steps. But if you observe, in our entire training process, we are fixing this learning rate. Okay, in our entire training process, we are fixing this learning rate. Okay, in our entire training process, we are fixing this learning rate. That means we are not adding any flexibility. Okay, we are not adding any flexibility to adjust this learning rate based on the training. Okay, based on the training and loss, we are not adding any flexibility to this learning rate to adjust itself. Okay, we are just restricting the learning rate. Okay, now to solve this issue, we have a small concept called learning rate scheduler. In this learning rate scheduler, what you do is you set a schedule. Okay, you take in this value for the schedule, and let's say for 10 epochs, for 10 epochs I want my learning rate to become 1 by 10 times. Okay, for every 10 epochs I want my learning rate to become 1 by 10 times. Okay, now let's say I have set my learning rate as 0.1. Okay, now after 10 epochs of training, my learning rate becomes 0.01. Okay, my learning rate becomes 0.01. After another 10 epochs of training, my learning rate becomes 0.001. Okay, in this way, after every 10 epochs, my learning rate becomes 1 by 10 times. Okay, but even there is an issue over here. Okay, here we are fixing the value of the schedule. Okay, this value of the schedule must be manually set. And another problem is, based on this number of epochs we are adjusting the learning rate, but not based on the loss. Okay, but not based on the loss. Okay, when the loss is higher, okay, when the gradient descent is over here, we need to take huge steps. That means when loss is higher, we need to take larger steps. But we are decreasing this learning rate based on the number of epochs. Okay, based on the number of epochs, but not on the training process. We are not decreasing this learning rate, not based on the training process, but we are considering the number of epochs as our criteria. Okay, this is the problem with learning rate scheduler. And another problem with this fixed learning rate is, we are fixing the learning. Okay, let's say our learning rate is 0.1. Okay, now if we have n number of weights, okay, if we have n number of weights in our artificial neural network, for all those n number of weights, we are making this 0.1 as a fixed learning rate value. Okay, to update all those weights, we are considering this 0.1 as a fixed learning rate value. Okay, to update all those weights, we are considering this 0.1 as a fixed value. Okay, means we are adding the restriction over here. Okay, we are adding some restriction over here, means we are not giving any flexibility to adjust the learning rate based on the weights. Okay, we are not giving any flexibility to adjust this learning rate based on the weights. Okay, we are just fixing the learning rate over here, means we are adding some restriction to our training process. Okay, this is our first two problems. And our third problem is local minimum. Okay, now let's say, yeah, this is our gradient descent curve. Okay, this point is called global minima, this point, and these 3 points. Okay, these 3 points are called local minimas. Okay, these 3 points are called, sorry, local minimas. This point is called global minima point. Now let us say a gradient descent as initially start from here. Okay, now it takes steps and reaches this local minimum point. Okay, after reaching this local minimum point, as the slope of this local minimum point is 0, the weights and bias are not updated at this local minimum point. Okay, the weights and bias are not updated at this local minimum point. That means what my gradient descent algorithm thinks is, this is my global minimum point and I should stop over here. Okay, the weights and biases that are present over here will be my optimum weights and bias values. Okay, the weights and bias values present over here will be my optimum weights and bias values. Okay, this is the problem of local minima. Okay, now when the gradient descent algorithm reaches this local minima, it thinks this local minima as the global minima and returns the optimum weights and, okay, weights and bias values at this local minimum. Okay, now the fourth problem is saddle point problem. Okay, this saddle point problem is also similar to this local minima problem. Yeah, now let us say this is my gradient descent curve. Okay, now I'm starting from here. Okay, when we start from here, I'll be taking the steps, and when I reach over here, okay, when I reach over here, you can see that there's an horizontal line. Okay, the curve is horizontal straight line. Okay, that means the slope over here, okay, the slope over here will be 0. Means as I move further, you can see that for n number of steps, the slope is being 0. Okay, the weights and bias are not being updated for even n number of steps. Means my gradient descent algorithm will think this point, okay, these points as the optimum weights and bias values points. That means it thinks this as a global minimum. Okay, it thinks the saddle point as a global minima and returns the weights and bias values over here. Okay, now due to this saddle point, the weights and bias values are not updated. My gradient descent will be stuck over here. Okay, my gradient descent will be stuck over here. Now to overcome these four problems, we have our optimizers. Okay, our optimizers that are designed to overcome this four problems. Okay, first is Adagrad, second is NAG, third is RMSprop, and fourth is adamoptimizers. In our further videos, we'll be discussing about all these concepts in detail. Okay, hope you like this video. If you like the video, please like, share, and subscribe. Thank you.